Amanda, Tavi, can y'all hear me?
Yes, sir.
Yes, sir.
Okay, very good.
Good afternoon, Tavi.
Hi, Amanda.
Amanda Panda.
That's right.
I feel like I'm forgetting something. Still got a few more minutes. Yeah, there's no projector. Did y'all get a chance to take a look at that review yet? Yeah. How'd it look? Is that good or no, not good? All right, am I sharing my screen? No, not yet. Y'all can see my screen at home?
Yes, sir.
Okay, good, good. All right, let's get started. It's 1 o'clock. We have an exam on Wednesday, right? So I will expect everyone to be present for that exam. Hey, come on in. I expect everyone to be present for that exam. So you'll come in, paper, pencil, good old-fashioned exam, and I'll be looking at your work. So make sure that you include steps because I will give partial credit. It's just, you need to have stuff worked out, all right? And that'll be all we do on Wednesday. You'll come in, sit down, give you the test, and when you're done, you leave, that's it. And that'll be it. That'll be our first test. Okay, so I sent out the review. I have not created the solutions to this review. I was thinking about doing it in a video, kind of like I do the homework. But that probably won't happen until this evening if I do it, right? So just keep your eyes open, be on the lookout for that, okay? And so if we have questions over the review, we can talk about that toward the end of class. I do want to continue on our schedule here. We are, let's see, we've done pretty much everything there. Okay, everything in yellow we've done. So today we're supposed to be doing quadratic functions and their graphs. We are going to be covering today graphing techniques and completing the square. We are going to do that, but it will not be on the test. The only way it would be on the test is if it was in the form of a bonus question, all right? So this homework assignment 3.5 was originally due today. I changed that due date. It's due on Monday, okay, on Monday. And then the other due dates for 4.3 and 5, I think I've moved those out also, okay? We good? I'm gonna get started with today's material. Let's see how quickly we can get through it. If we can get through it in a reasonable amount of time, then we can maybe start talking about the exam, all right? So today, this graphing technique stuff, really, I mean, this is a summary of what the section covers. Okay, now, without us getting completely into this, I wanted to just motivate the whole idea with a couple of examples, all right? So what we learned last time is that we have a toolbox of functions that we all need to know what they look like, right? X squared, x cubed, square root of x, a cube root of x, right? Absolute value of x, all these functions that we need to know kind of what the basic ones look like. And now this section is about what if we want to kind of make those look a little different? What if we want to move them up, down, left, right, flip them over, reflect them? stretch them out, widen them. How can we do that? How does that make the actual function look different when we see it on paper? So these are called transformations. And these transformations are valid for all functions that you'll ever see in your life, not just the ones we've studied last class. So let's start with an example. Let's take a very basic function, f of x equals x squared. And that is something that we should know from last class, right? We should all know what that looks like. Let me bring up kind of graphing paper here instead. We know that if you were to graph this, we could do the good old-fashioned t-table. This is not what we would do for every function. This is just for this one to kind of motivate the idea here. If we plug in 0, then of course 0 squared is 0. And so that's a point on our graph, 0, 0, which is the origin. If we plug in 1, right, 1 squared is 1. So that's another point, 1, 1. That means to the right one, up 1. Then if we plug in 2, right, we get 4. Square that, we get 4. Plug in 3, square that, we get 9, right? So 4, 5, 6, 7, 8, 9, that's way up here. And we already knew this coming in, that it would look like a U, right? Not a V. It would look like a U. Okay, and it continues to go up. So that's x squared. Domain, all real numbers, everything, negative infinity to infinity, right? Range, 0 to infinity. So what I'd like for us to investigate now is what would happen if I added a number to that function. So instead of graphing that, what if we tried this one? I'm going to call it g of x so we don't confuse g and f. What if I just take that x squared and I add to it, let's say 2? What would the effect of that be on the picture of the function? What do y'all think? Everything goes up 2, right? So it's like every y value that you used to have is now moved up 2. Now, if we did a t-table, and again, we wouldn't want to do this. If we did this, we could just check with a few points that if we plug in 0, 0 squared is 0, but then you add 2, right? So that's the point 0, 2. So that point right there, that used to be 0, 0, has now moved up 2. And now it's here, right? The point 1 gets squared. 1 squared is still 1. Add 2. Now that becomes 3. So that's 1, 3. So again, that point right there moves up. Instead of being up 1, it's now up 3. 2, 3. And then this point right here, which used to be 4, now goes up to 6. And I think you get the idea, right? The whole picture, where is it? Right there, right there, right? So the whole graph just moved up by 2, right? So what would happen if I subtracted 2 instead? Down. Okay, these are the easiest shifts that we ever could possibly have with functions, moving them up and down. These are called vertical shifts. All right, vertical shifts. And the idea is this, all right? Let me get to a new page. Well, you know what? Maybe we can just do it. Maybe we can just do it right here. Yeah, look, we'll just look at this right here. Let's look at that very first one. So let's say, now the way you read this table is this. Let's say you know what f of x looks like, okay? Like for us, we know what x squared looks like, right? This says, if you know what f of x looks like in yellow, and you add some number to it, then you're going to shift the graph up by that much. Okay, that's what that says. You understand that notation? The one below it says, all right, well, let's say you know what f of x is, and you subtract a number from it, then that's going to shift it down. Easy enough? Okay, up and down, just if you see a number out to the side, that's going to move it up or down. That's it. The tricky one is the left and right shifts, because those do not work the same way. First of all, they go opposite of what you think. Like normally, like for up and down positive number, like +2 went up 2, subtract 2 went down 2. But for left and right, it's backwards. If you add 2, you don't go to the right 2, you actually go left 2. You subtract 2, you don't go left 2, you go right 2. So it's opposite. Let me again motivate this with an example. Let's look at our original function of f of x is x squared. Now, what would happen if I compare that function to the function g of x equals watch x plus 2 squared? Notice where the +2 is, right? Notice that the +2 is not outside. Like the previous example, when I did the previous example, I did x squared plus 2 like this, right? The +2 is out to the side. There, the +2 is inside the parentheses before the squaring happens. And that's what designates, or that's what signifies to you that this is a left or right shift, is that the number's not out to the side. Now, I want to make a t-table because I want to convince you that this actually moves it to the left 2, not to the right 2. So let's try a table. What would happen? I'm plugging in x here. This is going to be x plus 2 squared. What happens if I plug in 0? So 0 plus 2 first, right? So the inside of the parentheses is still 2, and then you square it and you get what? 4. So you plug in, you get 4. What happens if I plug in 1? So you do 1 plus 2 first, that's 3. You square that, you get 9, right? Then let's not keep going that way. Let's go the other way. Let's go -1. What would -1 give you? So if you plug -1 in here, you got 1, right? -1 plus 2 is 1 squared. That would give you 1. What if you plug in -2? You get 0. Do you see that? That is an important point. So if I go to the graph of this, at -2 on the x-axis, my y-coordinate is 0. So at -2, my y-coordinate is 0. At -1, I went up 1. At 0, sorry, at 0, I'm at 4. 2, 3, 4. I should have had graph paper up here. And it goes like this. And then if we did more numbers on the other side, we'd see it goes like this. And can you all see that that is just the parabola moved to the left 2? Left. So if we had a -2 in there instead, it would move to the right 2. Got it? Sure? Okay, so let me go back to the notes here. And let's focus now on this. If you have a function and you add a number in green, if you add a number inside the function, that moves you left that many units. If you have a function and you subtract a number inside, then that'll move you to the right that many units. So do you see the difference in these two notations? It's subtle, but it's important. It's where the parenthesis ends on the x. Here it's the function, you're adding or subtracting a number. Here, the adding and subtracting is happening inside the parentheses. That okay? Okay, let's talk about, I'm going to skip down to the bottom. I think it's more natural to go to the next two. What would happen, again, if we start with f of x equals x squared, and we compare that to g of x equals negative x squared. So all I've done is I've thrown a negative into the front of it. That means everything that used to be positive now becomes negative, right? And everything that used to be negative now becomes positive. You're just changing the signs. So if the original function looked like this, where we had 0, this is the original x squared function, looked like that. That's x squared. If I do negative x squared, every single point that used to be positive now gets reflected down negative, right? So this positive point comes down, becomes negative. This positive point comes down here, becomes negative. And that's for every single point. So this would be a reflection. This would be g of x, or yeah, I'll do g of x equals negative x squared. So we could say that's a reflection over what? The x-axis, okay? So negative in front of the function is a reflection over the x-axis. right? What do you think a negative inside the function is? Not outside by itself. See that negative, this negative right here, -1 right here is outside the function. What would happen if I put a negative inside? I'm going to compare it. Let me do a green one. How about h of x? What if I put a negative inside the parentheses with the x and then squared it? What do you think that would do? Reflected over the y-axis. That would do a reflection this way. Now, it turns out for x squared, would it change anything? Wouldn't, right? Because x squared, isn't x squared an even function to begin with? So it is a reflection of itself over the x-axis. I mean, sorry, over the y-axis. So that shouldn't change anything. But again, the main idea here is to go back to this. And let's look at the bottom two here. If you put a negative, right, in blue there, if you put a negative in front of the function, you're going to reflect it over the x-axis. If you put a negative inside the function, you're going to reflect it over the y-axis. Any questions? So I'm going to give you one now, just to make sure you're okay with this. If I were to ask you, first of all, to graph this f function, okay? So this is a different f function, right? Let's go ahead and sketch that. So we would have to know what that looks like, right? And we all know what that looks like from last class. What does it look like? A V, right? And one of the things we need to remember is that it's not just any V, right? It's a very special V where the V forms here is like a 45-degree angle, because if you go over 1, you go up 1. Right? If you plug in 1, it spits out 1. You plug in 2, it spits out 2. So this should be a very, very nice, perfect diagonal like that. And then the other way, it's pretty much the same thing. That is what the absolute value of x looks like, right? So let's try this. G of x equals absolute value of negative x. Who wants to tell me what that does? Go ahead. What does that do? That reflects it over the y-axis because the negative is inside those absolute values, right? So that should be a reflection over the y. Now, does that actually change our picture? No. It doesn't, because this is an even function, right? But that would be a reflection over the y. So if I drew it, it would be right on top of itself, wouldn't it? So absolute value negative x, right, is going to be the same thing as the red one. Now, what about this one? H of x is negative absolute value of x. What's that going to do? Yep, bring it down, right? It's going to take the red one and flip it over. So now it's going to look like this. Still kind of a perfect diagonal, but it's the other direction. This is negative absolute value of x. That's terrible. Oh. Okay. What do you think this would be? J of x equals negative absolute value of negative x. It'd be a reflection over both, wouldn't it? Now, which one do you reflect first, or does it matter? We're starting to get into a tricky little spot here. Okay, so yeah, this is everyone pay attention, even if you're familiar with this and you're boring you, okay? The way we do this is critically important, the order we do it. And the way we do it is the same way we do order of operations. But the way that I teach it is to just think about, if I asked you to plug in a number for x right now, okay? Let's say I asked you to plug in something for x. Let's try something. Okay, if I asked you, let's say, plug in 4. You replace that with 4, right? If you were to tell me what that is, the first thing you would do is figure out what the absolute value of -4 is, right? That's what you do first. What's the absolute value of -4? 4, right? And then you would say, okay, well, then that's just going to be -4, right? So you could almost look at it like we worked from the inside out, right? That's the order we have to do the reflections. We have to start from the inside and work our way out. So the first reflection we would do is what? This one here, right? And that's over which axis? This one right here. That's over the y, because it's in the absolute value, right? So first I would reflect over y. Let me just draw there. So first I'd reflect over the y-axis. Second, I would reflect over the x. Now in this problem, it doesn't matter which order we did it. For this problem, it doesn't, but in future problems, it will matter. So if we took the red function, right, take the red function, reflect it over the y first, nothing changes. Reflect it over x then, and then it basically turns into the green one, right? So this green one is actually the same. H and j are the same functions if you were to graph them. Okay, y'all still with me? Everything good? Things are going to get a little weird here. Just see, because the idea here is when we start to put all of this together and have like a function that has multiple transformations and reflections happening all at one time. That's when things can get a little tricky. All right, we have one more thing to discuss on this chart, okay, and that is this idea of compressing or stretching. So you know how when we put a number in front of the function, see that negative number? That's really like -1, isn't it? And a -1 reflected over the x-axis, right? What if we change that number in front to something other than -1? What happens to the function? That's the next kind of goal. So we'll start back. Let's go all the way back to the original function we've been looking at here. Let's go back to x squared. And let's see what would happen if I take that and let's just multiply it by 5. 5 times x squared. So I'm not adding 5 to the outside, right? I'm not adding 5 inside. I'm multiplying by 5, right? I'm multiplying the x squared by 5. So if we did a t-table here, what would happen? So if we have 0, does anything change? 0 goes in, 0 squared 0, 0 times 5 is still 0. What about 1? Because when we used to plug 1 in, we would get 1. But now we get 5, don't we? What about 2? What did we used to get when we plugged in 2? We should get 4, right? But now we hit it with 5 again, and now it's going to be 20, isn't it? We plug in 3. Well, 3 squared is 9, but now we hit that with a 5, and that's what, 45? So I'm going to have a computer graph this for me because it'll be much easier to do. So let me graph y equals x squared. That is our standard. Zoom in a little bit here. That's our standard parabola, right? That's y equals x squared. Now we just did 5, right? 5x squared. So if I do 5x squared, here's what it looks like right there. That's 5x squared, right? Because when we plug in 1, where are we at? Way up at 5, right? And when we plug in 2, we're way up at 20. And when we're at 3, we're way up at 45, right? So what would you say, how would you say that changed the graph? Like if you had to explain it verbally to me. Compressed it, made it more narrow, right? Stretched it up. Do y'all agree both of those make sense? Compressed it this way or stretched it this way? Yeah, both kind of make sense. The way that the book describes it is that if you have a function, I'm going to do it in yellow again. If you have a function and you put an a, see that a in front of it right there? If you put a number in front and that a is a positive number, okay, like we just put 5, right? It says that means you multiply each y coordinate by 5, and that will stretch the graph vertically. Okay, it's going to stretch the graph vertically. That's the way they want you to think about it, right? It's only going to stretch the graph vertically if that number is bigger than 1, though. Okay, if the number is between 0 and 1, it's actually going to compress the graph vertically. So let me show you that. Okay, I want to show you what the compression looks like, a vertical compression. Go back to my graph here. I'm going to graph, let's go y equals, what number would you like for me to put in front of it? This is, the red one is 5x squared. This is x squared. What would y'all like to see? Give me a number between 0 and 1 so we can see what the vertical compression looks like. 0.5, half?
0.5.
You don't want to do half? 0.5? Okay, so I'm going to go 0.5 x squared. There it is. It's in black. Do you see that? They call this a vertical compression. That's what it's called, a vertical compression. Now, you might think of it as a horizontal stretching, right? I think you could do it both ways. Like me in my own mind, like I think both of those make sense. I'm just telling you what the book looks at, how the book looks at it. The book says if the number in front is positive and bigger than 1, it's a vertical stretch. If the number in front is positive and between 1 and 0, it's a vertical compression, which really kind of widens it. It's weird. I mean, you can literally look at it both ways. Okay, so what I've done here, I'm going to take those away. I've made this where I can play with the numbers now, okay, just so you can see it. I'm going to just change the number. This is our good old x squared, right? I'm just going to start changing the number so you can see what happens. Here's our standard x squared function. I put the number in front. This is a right here. Right now, a is 1. If I do a positive number bigger than 1, I start stretching it vertically more and more and more and more and more, right? If I go, hold on, I need to change this to, let's go 0.2. So if I start moving this, let's see, 4, I'm still bigger than 1. Here's the standard function right there. If I take a number between 0 and 1, look what it's doing. See that? That is a vertical compression. What happens if I let a be 0? It's gone, right? You don't have a x squared anymore. It's just 0, which is the uninteresting function because that is no longer a quadratic or a parabola. But what if a is negative? It's going to start going the other way. See? Negative. And then same sort of story on the other side with negatives. Here's our standard. This is if -1 is in front of the function. That was just this reflection, right? So if I put -5 in, it's going to stretch it vertically and flip it. So here's what -5 looks like. Right there. Okay? So the moral of the story is this. If you put a number in front of a function, right? If it's positive, it stays the way it was. If it's negative, it gets reflected, right? If the number's bigger than 1, it gets stretched vertically. If the number's between 0 and 1, it gets compressed vertically. And that's what this this table here is kind of telling you, all right? I think through my years of teaching, I think that this is the part that's most confusing to students, the hardest to actually illustrate and graph is the compression and stretching. All right, with all that said, let's do an example now where we have to put all this together, all right? So I'd like for us to sketch, let's do y equals -2 x plus 3 squared minus 5. All right. First thing we want to do is recognize which function is this that we should know, which from our last class, our library of functions, we all recognize that this is the parabola x squared, right? This is the square function. So we know starting off the very beginning that this is going to look like our standard x squared, but we're going to have to do a bunch of crap to it. So there we go. So we know that, and it's important that you draw it somewhat correct. See if I can select this. There we go. There we go. Okay. So the standard x squared looks like this in black. 1 at 2, it's up at 4, so it looks like that. Oh, crap. There we go. There it is. All right, that's our standard x squared function. All right, what happens first? Yes, so remember when I said the order we do things is critical? We act like we're starting, we act like we were an x, right? If I asked you to plug an x in there, what's the first thing that happens to you? You add 3, right? So that add 3 moves us left 3. So what I'm going to do is I'm just going to start writing down the things that are going to happen. The first thing that's going to happen, I'm going to go left 3, right? Let's write them all down first, then we'll actually do it. What's the second thing that happens? Well, technically you're supposed to get squared next, right? But that's giving us the basic shape. Okay, so we don't need to worry about that. What now? Yes, the -2. This multiplication would come before the subtraction, wouldn't it? So I'm supposed to reflect it over the x-axis, right? This is a reflect over the x-axis. And then what did you say? And stretch, which way? Yeah, vertically by 2. So we're going to just stretch it out by 2, right? Flip it over, stretch it out by 2. Are we done? The last thing is, the third thing we'd do is we'd move it down by 5. Does everyone understand the order that we did that? Any questions on that? Because there is a negative on the 2. If that were just the 2, forget the negative. If we're just 2, it would just stretch it by 2 vertically. But because it's -2, it flips it over the x and then stretches it. Does that make sense? Because the 2 is bigger than 1. Okay, so if that 2 wasn't there, it would just be a reflection. That's all it would be. But because it's -2, we reflect and stretch. If it was -10, we would reflect and really stretch. Make sense? What if it was -1/5? We would reflect
And go wider.
make it wider, or compress vertically. Again, it's weird. Stretching makes your parabola go like this, right? And compressing it makes it widen out. Okay, so let me try this. First thing I'm going to do is I'm going to take this picture and move it to the left 3. 1, 2, 3. I'm going to redraw it like this. Just a real quick dashed line. Okay, that's the picture so far. That's step 1. Step 2, I reflect it over the x-axis and stretch it vertically. Let me do those in 2 different phases. First, I reflect it, right? That's reflected over the x-axis. Stretching it vertically is going to make it more narrow, right? So I'm going to do that in different color. It'll go maybe more like this. With me? And then I take that picture just the way it is, and I'm going to move the whole thing down 5. 1, 2, 3, 4, 5. I'm going to run out of space here, but I'm taking that picture, which is now going to start here, and it's a narrow parabola like this. And that's the graph of this function. And just to label it, that's the point -3, -5, just so you can have a reference point. Make sense? What's the domain of this function? All real numbers. Because if you go to the left and right, you've got picture, don't you? What about the range? Other way around. Always move from like the bottom up. So negative infinity up to -5, including -5. I'm going to put that down here. The domain of that function is going to be everything. And the range of that function will be negative infinity up to -5, right? Including -5. Question, sir? Okay, so it would depend. I know exactly what you're saying. In your homework, okay, it gives you a problem where it tells you what to do and to come up with a function. Okay, so if I tell, let's do an example so you'll see what I'm saying. Here, this time, what I'm going to do is I want you to come up with a function. I want y'all to imagine that you had f of x was x squared. And I want you to come up with the function g of x, okay, which is basically that function f of x, but with these transformations, okay? I want it to go first. I want it to go down 3, then reflect over the x axis, and then I want it to go right by 2. Can you come up with the function that does that? That takes that picture, moves it down 3, reflects it over the x-axis, and moves it right 2. Right? So let me show you how this can be dangerous. Okay, what does the down 3 mean? I need to subtract a 3 at the end? Okay, we know this is going to be the x squared function, don't we? Okay, what does reflecting over the x-axis mean? Put a negative in front, yes? Okay, what does right 2 mean? X minus 2 inside, right?
-2.
Okay, got it? I'm going to graph that for you right now with the computer. You ready? I'm going to graph it. Let me go to a new graph. Did anyone write that down? It was negative x minus 2 squared, and then what? -3. Okay, and then the original function is x squared, right? Okay, so what did I tell you to do again? You're supposed to go down 3, right? First, you're supposed to go down 3. You're supposed to go down 3. So 1, 2, 3. That's this picture, isn't it? Then what? Reflect over the x-axis. What does that look like reflected? Up here, it looks like this, doesn't it? And then you're supposed to go which way? Right 2. That means what I wanted was that one. And you gave me this one. Do you see what I mean? You have to be really careful because it's not just like, oh, look at the transformations, just make them happen. You have to, the order matters. So let's go back to that problem and let's do it again because this isn't right. What we did wasn't right. Do y'all understand? Okay, let's go back and let's see how we could have made this right. Okay, so this doesn't work. Okay, I want to go down 2, right? I want to go down 2 first. So what I'm going to do is turn it into x squared minus 2, right? That'll make it go down 2. I'm sorry, down 3. Apologize. Down 3. Okay? That will move it down 3, right? Then what do I want to do with that? The whole thing, right? I want to reflect it. So what I'm going to do is put a negative in front of the x squared minus 3 like that. That will take that whole picture above it and it'll reflect it over the x-axis. Why? Because putting a negative in front of a function flips the whole thing over, right? Now what do I do with that?
do you want to add 2 instead of subtract 2?
No, you
Because it's
still,
the
you still want to
opposite.
move left and right is still going to be the opposite of what you think. So let me clear that out of there. There we go. So we still want to subtract 2, but inside with the x, right? Yep, you're going to do negative. Then you're going to do x minus 2 squared minus 3. So again, this moves the graph down 3. This reflects it over the x-axis. This shifts it to the right 2 because I subtracted 2 inside with the x. Now, one thing you could do is multiply the negative through. If I multiply the negative to the first thing, I get negative, then x minus 2 squared. And then the second one, I get plus 3. We cannot multiply this negative in through this parenthesis. Cannot do it. Why? Order of operations. Exponents go before multiplication. So you cannot change this to negative and positive. Negative x and positive 2. Cannot do it. So if I graph this, maybe, right? Maybe. Let's try it. It was negative, in parentheses, x minus 2 squared, right? Plus 3. Okay. Is that it? Yeah, I got to put the original one here. Here's x squared. There was x squared. First thing we did was moved it down 3, 1, 2, 3. It was 3, right? Yeah. Down 3, that was this. We reflected over the x-axis, which now makes it this. And we move it to the right 2, and there it is. See what I'm saying? You have to be kind of careful with this.
Specifically, looks like it doesn't matter whether you shift it right or left, up, down.
For the even functions, yeah, it doesn't do you mean this shifting doesn't matter?
Shifting doesn't matter. The reflections, like the order in which you reflect it, do all that matter. Looks like you could have added, like, could have shifted left before you shifted it.
Well, as long as there isn't a y-axis reflection.
That's what I'm saying.
Yeah. So if there's a y-axis reflection in there too, like let's take these out of here. Let me clear this. No, I want that one. Like if I tell you to take this one, move it to the left 2, right? Up 3, then reflect over y, then reflect over x, right? Then everything matters. So I guess you just have to be careful. I mean, it's the hardest is when they give you a set of instructions of what to do and you having to generate the formula from it. That's the hardest, I think, because you have to pay attention to where parentheses are. If they just give you the function, I think that's always easiest because you just start from the inside and work your way out, which we should do more of. Let's do another example of this. So how about this one? F of x equals, let's do an absolute value. Let's do negative 1/4 absolute value of negative x plus 2 plus 3. This is a, you know what? We're not ready for this yet. Let's get rid of the negative in front of the x. That negative in front of the x, let's get rid of it because we'll do that on the next one, okay? So starting from the inside, work your way out. That plus 2 means move it to the left 2, right? So we're going to do, first step, we're going to do left 2, okay? Then the absolute value, which is going to give us our V shape, right? All right, so we already know we're going to get V shape. Second thing that's going to happen is, well, what does the negative 1/4 mean? Right? Reflect it over the x-axis. Reflect and compress it, x-axis. Compress vertically, right? which really widens it, doesn't it? So it takes that V and just kind of stretches it out like this. And then up 3, right? All right, so let's graph it. Start out with your basic good old-fashioned absolute value, which looks like this. And now we start cranking it out. So first thing, move the whole thing to the left 2. 1, 2. Now it looks like this. Then reflect it over the x-axis and compress it vertically. So here's the reflection over the x-axis. Goes now, the V looks like this. Right, over the x-axis. And then compress it vertically. So this, I'm just gonna kind of eyeball this. I'll do it in black. I'm gonna just kind of illustrate that I'm not doing it dash because I want you to really see like that's my version of the compression, okay? It's stretched it horizontally, or you can say compressed it vertically. And one more thing, right? That whole picture up 3. So I like to just take that point, move it 1, 2, 3 right there. And then this would be it. See, and once you have that picture, you can say domain, range, everything's pretty easy to see. Well, I hope it's easy to see. Domain is everything. Range is negative infinity up to 3. Questions? Good. All right, now let's do the one with the negative in there. Okay, that negative, I took it out on purpose. Let's see why. So what if we did f of x equals negative 1/4, absolute value, negative x is plus 2, right? Plus 2, plus 3. Okay. One way, I think that, I don't know, how would you interpret this? Reflect over y. Let's just write it down first and let's see if it's right. First thing, reflecting over y. Why are you reflecting over y? Reflect over the y-axis. Because the negative in front of the x, right? That seems reasonable. Okay. Second thing. That plus 2, right? Which should mean left 2, yes? Because I've told you that when you're working these, you always start with the x and you kind of work your way out from there. Just as if you were plugging a number in. And if you have a negative in front of the x, that's supposed to give you a reflection over y. If you have a negative out front, that's a reflection over the x. Is that okay? So this gave us reflection over y, we think, and then left 2. Okay, what would come next? Yep, so the negative 1/4 would give us the reflected over x, and then vertical compression, we think. And then the last thing, the fourth thing would be up 3. Up 3. Let's draw it and see if it's right. We'll draw it and then we'll graph it on the computer and we'll see if it's right. Feel good? I'm going to go to the computer now and I'm going to go ahead and clear this out. I'm going to draw it on here. We were supposed to have our absolute value function that looks like this. And we said what first? Reflected over the y-axis, right? Which doesn't change anything, does it? Not for this particular function. Reflection over the y. Okay, then what? Right, was it right 2 or left? Left 2. So left 2 puts us here. That's our left 2. Then what? Reflection over the x-axis and vertical compression, which should make it a little bit wider, like this, right? And then what? Up 3. 1, 2, 3. So something like us. The straight lines are great. It should be that one, right? This one right here? Okay, let's type it in. It was -1/4 absolute value of negative x plus 2, right? Plus 3. Oh, shit. That ain't it. So what happened? See, something is tricky. These y reflections are always tricky. The x reflections are not tricky. What's that? We reflected it to y. How the hell are you going to know that though, right? Like how, because we followed what we've been doing. Start with the x and work your way out. There's one kind of exception to the rule, all right? And that is exactly when you see a negative in front of the x. Okay, so I'm going to take you back to this, and I'm basically going to tell you this is all crap, all right? And it's because that negative in front of the x. So here's the way we resolve it, okay? What we do is we say -1/4 absolute value. You see that negative in front of the x? We're going to factor the negative out of the x. So I'm going to put negative parenthesis x minus 2 close parenthesis absolute value. You see what I've done? I've rewritten this like this. Do y'all agree that's the same thing? Negative would come through and become this. See that? You only have to worry about that if you have a negative on the x. It's the only time you have to worry about it. And then we have plus 3. Now, how does that change our steps? See, these are the steps we canceled out. What are our new first step, second step? So what's the new first one? Start in there with x, right? Right 2. Right? Right by 2. Then second step. This moved us right 2. Then we reflect over the y. Reflect over the y.
And
Now
that's
move it-
for the,
Go ahead.
oh, I'm sorry. And that's because of the negative being factored out of the x minus 2.
That's right. So order of operations would say we have to do what's in parentheses first, right? So that would be -2 inside means move it to the right 2. Negative means reflect it over the y. Now we do the -1/4 out front. Does that make sense, Amanda?
Yes, sir. Can I ask one quick question?
Uh-huh.
Why would we factor out the negative and not just do, because like the absolute value, I guess, of I'm obviously I'm wrong here, would be the opposite of a negative.
Because we're trying, so I understand what you're saying. The absolute value of a number is going to spit out positive no matter what. What we're trying to do is rewrite the function in a way that we can use the transformations, see what the transformations are going to be without taking. Are you saying that the absolute value of that negative is going to kill it off anyway? Is that
I
what
think
you're saying?
so. I think
Yeah,
so. Same
well-
thing as I did with the addition. I kind of just jumped ahead, I think, turning the last problem, the -3. I kind of already knew it was going to be an addition.
What -3?
On the last problem we had, the last graph, when we were, or yeah, so when we,
Was it this one?
no, the one before it. Yes. So when we factored it, I kind of already knew it would be to the right 3.
This one wasn't right 3 though. This one
Oh,
was
I'm sorry,
down.
left 3.
See, this one was right 2, down 3 because of the -3
Yes.
here.
Okay. Yes. So it was going to be up 3.
I'm not quite sure. following
I
you.
know I'm getting yeah.
So these are two different concepts. This concept is I give you what I want you to do to the graph. You come up with the function.
Okay.
As opposed to I give you the function and you tell me what's going to happen to it.
Okay, and it won't necessarily follow the same set of
It does follow the same set, except when there's a negative in front of the x. When there's a
Okay.
negative in front of the x, you must factor the negative out of that entire expression like this,
Okay,
and then start over and go, okay, do this first, then the reflection over y. That would be this negative. And then we do the next thing out here, which is our reflect over x with vertical compression. And the last thing is up 3. Yay or nay?
yay.
Let's go back and see if it works this time. Okay, so does this work? So where do we start? Oops. Oh, come on. Pressing the wrong buttons. Okay, this is our original, right? Okay. So is this going to work? Let's do it and let's see what happens. Right 2, right, like this. That's right 2. That's the first thing we're supposed to do, right? Then what? Reflect it over the y. Oh, shit. What's that going to do? That's going to bring everything over on this side right here like this, isn't it? Then what? Reflect over x. Then a compression. Oh, wrong color. And then up 3. 1, 2, 3. Crap, we're still not there. Do y'all see that? What the heck is going on? This negative in front of the x is the trickiest thing out of all transformations with functions. It gets everybody. Because if the negative's not there, everything behaves the way you want it to behave. Everything's nice. But when the negative is in front of the x, things fall apart. Okay? So yeah, go ahead.
I know this isn't really mathematically correct, but with the negative x, we can just do the problem and assume it's precisely on the other side of the y.
I guess that would be one way you could try is like, I'll just do it this way and then just reflect it. How about we do this? How do we need to look at it to make it go there? Think about what has to happen. We start with this, and I don't mean to sit here and give you an example that confuses you, but this is the most confusing part of all of it. So we need to understand this. We start with that. How can I get to this? We need to shift to the left before, don't we? We need to somehow come this way, right? And then do over the y-axis, then do over, and then do up, right? So let's do that again. We have to go here, then reflect. Let's go back and look at the function. How can we make that happen from this picture? Go back to this, right? Factoring the negative, do you see here with the negative factor, this still is forcing us to the right too, isn't it? So this isn't going to work either if we look at it this way. So we have to do it this way, right? With this +2 to make our left 2. But we have to do that before we do the y. And that it's just very unnatural. And so this is the trickiest one. So why don't we do this? Let's clear our minds. Let's do a completely new one and see if now that we kind of know that, we can just make it happen. All right. We're gonna do 2. We're gonna do let's go 2x plus 4 squared minus 3, and then we're gonna do another function which is almost the same, 2 and then negative x plus 4 squared minus 3. The key difference between these two problems is that negative right there. That's the only difference, right? So if we don't see a negative on the x, everything is beautiful. It works the way we would hope. First step on the red one is left 4. Okay, great. Second step. What does the 2 in front do? Well, it doesn't flip it over, right? It's just a vertical stretch. So this is vertical stretch. All right. Third step. Down 3. All right. How about the next one? Gosh, I hope this works. The next one, we have to recognize that we've got a negative in front of the x. Go, this is that one that's tricky. So I'm actually going to do this first, right? Which is left 4. So I'm going to go left 4. Then what?
Reflection.
Then the reflect over the y. Then what? Vertical stretch. And then what? Down 3. All right. Let's do those. I'll have to reference this up here. All right, clearing this out, clearing this out. Get rid of all this. Okay, so graphing the first one, we're going to do the one in red first. We started with the parabola, right? And then what do we do? Left 4. Then what? Vertical stretch just makes it more narrow, right? And then down 3. 1, 2, 3. Here we go. It's going to look like this, roughly. Understand? Okay, let's check it. That function was the function 2 parenthesis x plus 4 squared minus 3. There we go. Okay, not bad, not bad. All right. Domain range, we're in business. The other one. I'm on pins and needles here. Okay, so what we're supposed to do, start with this parabola again, right? And then we're supposed to go left 4, right? 1, 2, 3, 4. That puts us here. Now, reflect over the y-axis, which puts us here. Is that clear, everyone, for the reflection over the y-axis? It goes like this, like that, and then vertical stretch, which makes it more narrow, and then down 3. 1, 2, 3, like that. What do y'all think? Think so? Negative x plus 4 squared minus 3. Did I? Hold on, I can't see. Minus 3. Yes. Okay, so it's tricky. The negative in front of the x is tricky. Everything else, just treat it nice, up, down, left, right, reflect, do it all in the order of working from the inside out. The negative in front of the x, all you have to do is do the shift first, then the reflection over y, okay? Shift first, then reflect. Understand? I remember as a student, that negative in front of the x drove me absolutely crazy because it's so tricky. Should we do one more? How about I give you one to do? Okay? I'll give you one. And once you got it, you got it. It's not that bad, but it's remembering it, right? So when you get to Cal 2 and you have to graph something, you're like, oh, crap. Okay, here we go. So why don't you sketch? Sorry, I've got too many windows open here. Why don't you sketch? Okay. F of x equals -5, and work together if you'd like, square root of x minus 3 plus 2. And then I want you to do g of x is -5 square root of -x minus 3 minus 2. And you know what? We'll do that. I changed this one to a minus on purpose. Okay, because I don't want you to do the first one just reflected over the y-axis. Okay. All right. Let's take a couple of minutes to do that. All right. I'll let you, and feel free to talk to one another. I encourage that. Once you have them, I guess we can check. We'll check them. If you get them though, if you finish, try and find the domain and range of each one. For you at home, I'm gonna take a quick break. I'm gonna mute the microphone. I'll be back, okay? Y'all doing okay at home?
Yes, sir.
Okay. Anybody need help? Do you understand that now with that? No? Okay. Okay, so you have to know what the square root function looks like to start. Yep, okay. So tell me on the first one, you have the square, you have x minus 3, right? Do you see negative in front of the x? No, okay, so everything's gonna work as you would hope it would. So what does minus 3 inside there do? Right 3. Okay, so go ahead and just move that picture to the right 3. There you go. Okay, now work your way out. Don't do plus 2 yet. You have to do the -5. So what does that do? Flip it down, and then the 5. So the negative flips it. The 5 makes it what? Stretch vertically. So instead of being it's kind of hard to draw it, but so like you did this, right? And you're going to reflect it over X, but you're going to stretch it. So now it's going to go like this. So every point just gets taken down further down. That makes sense. Now it's not like moved down, it's stretched down. So this point, this anchor point stays. And then was there one more thing? +2. So what does that do? No, that was, you already did the left and right. So +2 on the outside, that's just the whole picture up 2. So this point goes up 2. Every point goes up 2. So now your picture is more like this. Yeah, let's walk through these. First one, the transformations here. First transformation here was that -3 underneath, right 3. It's a square root function, so we have to know what it looks like, right? Then the -5 out front. Reflect X. Vertical stretch. Third, up 2. Right? That's what we're going to do there. Right 3, reflect over X, stretch it out vertically, move the whole thing up 2. The second one, we've got that minus in there, right? Got that minus in there. So with the minus, this is the special one. What do we do first? This one first, right? Right 3, right? Right 3. Then we do that negative in front of the X. So this is the first thing, this is the second thing. So that's going to be what? Reflect over the Y-axis. Third.
Down 2.
Nope, third, take care of the -5 out front. Because this is multiplication, Amanda. So we do multiplication before we do subtraction.
Yes. Okay. Sorry.
Okay, so we've got X-axis, right? Reflect. Reflect over the X-axis with a vertical stretch. Geez, okay. And then finally, now, down 2.
Will there ever be any instance where you're going to vertically shift the graph before last?
Mm-mm. Up and down shifts are always the last things that happen. Yeah. Because adding a number on the outside, all it does is moves all your Y coordinates up or down. All right, let's see if we can graph these and see if it matches with what the computer says. So starting with the first one, let me clear this out. Okay, so I'm going to zoom in here a little bit. So we should be starting with the square root function, something like that. And then we're supposed to go left 3, something like that. We're supposed to go reflect it over the X and stretch it. So here's a reflection over X. And then stretched will probably make it look like that. Right? So here's reflection over X. Here's the stretch. And then that whole picture, what? Wasn't it up 2? Up 2. So up 2 units. So I'll do this. Every point moves up 2. So that X-intercept moves up 2. And then it's that vertically stretched version right there. So that should be it right there. That darker one. Let's check. -5 times the square root of X minus 3. Oops. And then what is it? +2. Oh, you know what? When I moved to the right 3, I accidentally moved. I didn't move over far enough. That was 2, right? See what I'm saying? I went to 3 right here. I don't know why I went. I was supposed to go to the right 3, right? Which would have been here. Let me go over it again. Let's clear this, blast that. Okay, started with the square root function. to the right 3, which puts us here, reflect over X, stretch it, right, up to there. So it was right. I just didn't move over to the right far enough. Okay, let's do the other one. So the other one was, I got to get back up to my notes. So we're going to take the square root function. We're going to go first to the right 3, which puts us here. Reflect over the y-axis. This is the critical one. Everything that was here gets reflected over there. So that's going to make it look like this now, right? See that reflection over the y? I didn't go far enough, did I? No, yeah, that's good. Reflection over y, and then reflect over x. Oops. I accidentally erased. Reflect it over x. Stretch it. And then what? Down 2. Which should move it down like here and then stretched out. So I should expect something like this down here. Drum roll. -5 square root of -x. What was it? -3. And then -2. There it is. It ain't perfect, okay, but you can see it here, right? It goes like this. Yeah, so those are tricky. Those ones with the negative in front of the x are tricky. Any questions? Right and left. What, shifting? Well, that's kind of the idea here, is that it depends. If you have this, right, you're going to do that right or left shift went first, right? Here, it went first, right? So yeah, I guess you could say that, but you just have to remember that when the negative's here, when you do this shift, this reflection would come out. I guess if it helps you, you could just say do it first. Yeah, just do your left to right shift first. Because no matter what, if you have to do a reflection here, that'll always come after this. Okay, it's 2:15. There are a couple of problems on the homework I think you can figure out. Let me just give you one example. They say something like this. Let's say you have a function f of x, and they tell you that it has x-intercepts at, let's say, x equals 2 and 5. Okay, they tell you that. So what they're telling you is you have some function where if you go to 2, you have an x-intercept, and if you go to 5, you have an x-intercept. They ask you, what are the x-intercepts for f of -x? So if f of x hits these 2 points, f of -x is this function, but with what? What does -x do to our function? Negative inside. Reflects it over the y-axis, right? So these 2 x-intercepts now get over here like this, right? So that should have x-intercepts at -2 and -5. Make sense? What if you say, what are the x-intercepts of f of x plus 3? Well, what does f of x plus 3 do to that original function? Move everything to the left 3, right? So this x-intercept now becomes what? -1, and this one, 2. You see, everything moves to the left 2. And then they go further. They say, like, they give you another one where they say, oh, between 2 and 5, they tell you the function is increasing. Like this. What if I told you between 2 and 5, the function was increasing? Then what about f of -x? What could you tell me about what's happening between what? -5 and -2, it would be what? Decreasing. See how you do with those. Those are a little bit tricky, but just see how that you do with them. I need to get on to a different topic that's more important, and I've got 22 minutes to do so. And that is something called completing the square. So we are stepping away from all this. And we are talking about something called completing the square. So I was in my Cal 2 class this morning here on campus. And I'll even bring up the notes so you can see it. We were doing a problem right here. This is the last problem we were doing. And we were looking at this quadratic right here underneath this radical. And I said, okay, to do this problem, we're going to need to complete the square. And so, where was it? Right here. We completed the square right here. I don't think anybody in the class knew how to do this. I was shocked, actually. I was shocked because completing the square is something you should learn here. So, you know, some things we see down the road, some things we don't. Completing the square we see again. All right, so this is an important topic. So the whole idea behind completing the square is this. You start with a quadratic expression. So everyone here has to know what a quadratic looks like. Ax squared plus bx plus c. All right, that's a quadratic expression. Now, normally here, a, b, and c are numbers. Okay, they're just numbers. So a specific example of this, as an example, let's do, do I want to do that one? That one's a little bit harder. Well, yeah, let's do something a little bit easier. How about this? X squared minus 4x plus 7. Let's do that. Okay. That's a specific example of a quadratic. All right. To complete the square, what that means is we're going to rewrite this. Okay. We're going to rewrite and we're going to make it look different. And the way it's going to look is this. It's going to look like a in front, x minus h squared plus k. Somehow we are going to transform this quadratic expression into this quadratic expression. The process of doing that is called completing the square. Now, just show of hands, how many of you have seen this before in the past, maybe? It kind of sounds familiar to some of you. Okay, so I will just warn you ahead of time. There's different ways to show this, and the way that I'm showing it is the way that will keep you safe in Cal 2 or in Cal 1, in both of them. There's a way to teach completing the square where you can get yourself into trouble if you're taught, not the wrong way, but it's kind of, how do I make an analogy? I'm terrible with analogies. What if I gave you a saw that only worked on one type of wood, right? That would be very limiting, right? I'm going to try and teach you completing the square in a way that it's like giving you a saw that works on every type of wood. All right. Now, as I do it, maybe you'll see what I mean. If you've seen it before, you'll see the difference. Okay, so how do we do this? How do we complete the square? First step is you must look at the number in front of x squared. Okay, that first step there is to make sure that the number in front of x squared, which is called the coefficient, is 1. Now, if it's not 1, I'll show you how to handle it, okay? But for the first example, we're just gonna stick with this. It's 1, right? So the number in front of x squared is 1, right? Okay, the next step is to look at the number in front of x, which for us is what? What's the number in front of x? And the minus, right? We take the -4. So you're going to take that -4. Anyone know what you're supposed to do with this? Take -4, that number that's in front of x squared, or sorry, in front of x, take that -4, you will divide it by 2. Every single time you do completing the square, you'll always take the number in front of x, you'll divide it by 2. Now, what does that give you? -2, okay? So we have what I refer to as our first magic number, okay? I put a little star there. That's our first magic number. Now what you do is you take that number that you just got and you square it. Every single time you will square it. So you take -2 and square it, and now that gives you the number 4, -2 times -2. And that is our second magic number, all right? So I put 2 stars next to it. Now, what we do next is weird. We will rewrite the original problem, okay? I'm going to rewrite the original quadratic right here. And what I want you to see, and you can either agree or disagree with me on this, is that right next to that 4x, right after that 4x, there is a +0, and then there's a +7. Do y'all see that hidden 0 right there? I mean, does anyone disagree that this is the same thing? I mean, that's the same thing, isn't it? If I take that and add nothing and then add 7, that's the same as adding 7, right? And that seems ridiculously dumb for me to do that. But this is the whole key to completing the square. Now what I'm going to do is I'm going to take that, and instead of 0, I'm going to add the 4 and immediately subtract the 4. Now, if you've learned this in a different way, what you were told was you add 4 to both sides of the equation. Does that ring a bell? Add 4 to both sides now? The thing here is we don't have an equation. There's no equation here. So there's nothing to add to both sides of anything. So that's why we realize a hidden 0. Now, again, does anyone disagree with me that 4 take away 4 is still 0? I mean, this is still the same thing, right? It's crazy what I'm doing, but it is true, right? Yep, still add the 7. So y'all agree that's the same thing? Now, by design, the first 3 terms of this, the first 3 terms are guaranteed to factor. Absolutely always, every single time will factor. In fact, it's what we call a perfect square trinomial, which means it'll factor into something times itself. And in this case, it'll be, does anyone know what 2 factors would multiply times itself to get that?
-2.
I asked you to factor this. What would it be? I think I heard
-2.
x -2 times x -2, right? If you multiply x -2 times x -2, you would get this. So isn't this just x -2 squared? Now, if you weren't sure what this turned into, what you can always do is put the parentheses in the squared, put an x, and then guess where that number always comes from? That first magic number is always the number that goes here, okay? Every time. So the green represents those first 3 terms. What do we still have? -4 plus 7,
+3.
which is 3. And do you see now that we have transformed this quadratic from this form to this form? Yes? Yes. Because this x -2 squared is not true if we don't have that 4 there. See, this right here is, well, do it on the side. What's x -2 times x -2? So we go here, that's x squared. Here, that's -2x. Here, that's -2x. Here, that's +4, right? That's x squared minus 4x plus 4, right? That's the first 3 terms. If you didn't have this 4 here, right? If that 4 wasn't there, then you wouldn't be able to say this. You couldn't say that this becomes this, right? You need the 4 there to be able to do it. And then whatever's here, -4 plus 7, that's just whatever's there. I mean, it's always the first magic number. Yeah. The second magic number is what you're going to add and subtract. So the first magic number will appear here. The second one is the one that you use to add and subtract. We'll do another example, but here's what's cool about this. If I asked you to graph this, could you graph it? Quickly, right? This is a parabola, right? You know, it looks like a U. Right 2, up 3, you're done. You've got the graph. See what I'm saying? Now that's not the way we use it in Cal 2, but here at this level, that's easy to sketch it now. Make sense? All right, let's do another one. Y'all want another one where the number, yeah, let's do another one where the number in front's 1. Okay, so I want you to complete the square on this. X squared plus 6x minus 4. By the way, for those of you who are like really good at factoring, the ones I'm putting up here can't be factored. I'm putting them intentionally so they can't be factored. All right, so here we go. Complete the square. So first thing you do, check to make sure you got a 1. You have a 1 in front? Yes. Okay, so now we take the number in front of x, which is positive 6 divided by 2. 3. That's our first magic number. Take that number. Do what with it? Square it. That gives you 9. That's our second magic number. With me? Rewrite the quadratic. Now the 0, right? So you go x squared plus 6x. Now you go, you always do the plus first. Plus 9 minus 9. You cannot do minus 9 plus 9. It won't work that way. Okay. The first 3 terms guaranteed are going to factor, and I don't even have to think about this. It's going to be x and then plus 3. That's the first magic number because the first magic number was positive 3. I put that in the parentheses, and then the only thing left here is what? Negative 13. So negative 9 take away 4, so negative 13. There we go. We've completed the square.
So
We'll put
the
a
only
number.
time
I
you
want to
use
do.
the
I want to do one more before I do a number in front. Is there a question online?
Yeah, the only time you use the 3 is just to square it.
Yeah, that part right there. Well, you need the 3 to come up with the 9 also, right?
Yeah, that was my question. The 3 to square it and then equals
That gives you
9.
9.
We
That
get
gives
the
you what
second
you
number.
add and subtract. And then when you go to rewrite this, that 3 is going to be helpful again because it gives you what goes in the parenthesis.
Okay.
Now, if you don't believe this is true, just FOIL this out, subtract 13, and I promise you, you're going to be back at the original thing. Okay, it's just another way of writing it. All right, so far everything I've done has been, I've been nice because I've kept everything clean. All right, is the number in front of x squared 1? Yes. Okay, what's the number in front of x? Negative 5. What are you supposed to do with that number? Divide, okay, so it's a fraction, right? I divide by 2. I'm not going to get my calculator out. I'm not going to do decimals. I'm just going to say, well, that's my number, okay? It's a fraction. My first magic number is a fraction. Then I'm supposed to take that fraction and do what with it? Square it. Okay, now I can square a fraction. I just multiply top and bottom or square top and bottom. So what would that give you? 25 over 4. Okay, so 25/4. That's my second magic number. That's what I'm going to add and subtract. With me? So I go x squared minus 5x. Here comes the hidden 0. Plus 25 over 4 minus 25 over 4. Then I still have the plus 1, right? The first 3 terms, guaranteed, are going to factor using that first number. X minus 5 over 2, that quantity squared, right? Now, what I still need to figure out is what this is, right? What is negative 25 over 4 plus 1? So I'm going to do that up here, negative 25 over 4 plus 1, right? But I'm going to get a common denominator. So I'm going to rewrite 1 as 4 over 4. And then I can just add straight across. So I get negative 21 over 4. Yeah? Yes, you could. But as we progress in math, we stop using mixed numbers. Yeah, just trust me, in calculus, we never, ever use mixed numbers at all because they're hard to work with when we start doing things. We do a lot with fractions, a lot in calculus. So it's easier to work with the proper and improper fractions than the mixed number form. Yeah. So that's it. That's completed the square. Again, if you don't believe it, multiply out that, square that out, subtract the 21/4. I promise you'll get back to that original thing. All right, you ready to see one with a number other than 1 in front? You don't want to do the one, let's do my calculus one that they couldn't do today. Okay, so here we go. See, the number in front of the x squared is not 1, right? So don't go getting magic numbers yet. You have to make it a 1. You cannot divide everything by 9 because it's not an equation. You can't work with both sides of anything. So what we do instead is something you can always do in math, and that is factor 9 out. This is kind of weird, but I'm going to factor 9 out of the parentheses, or out of the terms. My first term will be x squared. Y'all agree with that? Because if I multiply that 9 through, I'll get 9x squared, right? The second one, though, see, 9 is not a factor of 6. So, like, how did I pull a 9 out? Well, you can always do this. I just have to write plus 6/9 x, then minus 8/9. Now, all I did, if you think about it this way, all I did to figure out what these were is divided each of these by 9. So 9/9 is this, 6/9, 8/9, and check it for yourself. Distribute that back through, and you're going to get back the original thing, right? Now, I'm going to clean this up just a little bit because 6 divided by 9 is actually 2/3. Right? All I did was reduce that fraction. And we can start going to town on this. All right? Here we go. We take the number in front of x. And we take half of it. Oh, crap. How do you take half of a fraction? Yeah, if I take 2/3 and I divide it by 2, that's the same as taking 2/3 and multiplying by the reciprocal, which would be, what's the reciprocal of 2? 1/2. 2/3 divided by 2 is the same as taking 2/3 and multiplying by 1/2. Do y'all agree with that or not? This is one of those subtle things. Let me put the 2 as 2/1. 2/3 divided by 2 is the same as 2/3 divided by 2/1. Division of two fractions is the same as multiplication of the first one by the reciprocal of the bottom one. And now the 2's cancel, you just get 1/3. That's your first magic number. What do I do with that? Square it. 1/3 times 1/3? 1/9, right? Just multiply straight across, or square the top and bottom. Square 1, 1 squared is 1, square 3, 3 squared is 9. So here's where we are. 9 x squared plus 2/3 x. Here comes the hidden 0. Plus 1/9 minus 1/9. Then I still had minus 8/9, but that all still lived in a parentheses. All right. See how I'm keeping that 9 out here? I'm just redoing everything on the inside. The first 3 terms, guaranteed factor, right? To be x plus 1/3 squared. Yeah, so minus 1. So now we have minus 1/9 minus 8/9. Luckily for us, they have the same denominator. So that's minus 9/9. So that's minus 1, right? All of that's in parentheses with a 9, right? One more step. Let's distribute the 9. What I mean is the 9 will hit this and hit this. So we get 9 times x plus 1/3 squared minus 9. That is the completing of the square. By the way, you cannot distribute that 9 through this parentheses, right? This 9 right here cannot go through this order of operations. You have to square this parenthesis before you can pass the 9 through. So we just leave it out front. And that's it completed. So this whole thing about like the magic number and square, take that number, take half, then take that and square it. That, like, why we do that is, you know, someone figured that out and we just use it. It's very, very helpful. Okay, that should get you through the homework, okay, which isn't due until Monday. Now it's time to just focus on the exam, which I haven't had any chance to really talk about here today. The exam that's on Wednesday. So the review is going to be, the review is very long compared to what the exam will be. I mean, I'll make it where you should be able to finish it in an hour, 40 minutes in here. But everything on here is fair game in terms of what I could ask. So I went through, I looked at your homework problems, I looked at things that, you know, and just kind of picked. What I didn't do is put each section, what they came from. But these first few are from the review section. And then this is all review. You know, the sections that were called like R3, R4. Okay, that's most of this is review stuff. And then once we get to 7, 8, 9, this is where we're solving equations. And then this is where we're finding domains, difference quotient problems with various expressions. Some of these are easy, some of these are complicated and hard. And then given a graph, there's a bunch of stuff that we talked about. If I give you a graph, you know, even, odd, ask you for the function's value at a certain point, ask you when is the function equal to a value, x-intercepts, y-intercepts, domain, range, increasing, decreasing, local max, local min. I didn't feel like drawing like 5 different graphs. I just picked one that kind of had a lot of characteristics. I would just make sure you review your homework and what we did in class. My intention, though, is to have the solutions to this up, hopefully tonight. Is it Monday? Yeah, so it's Monday. I can maybe watch football or just have it on in the background and do this real quick. So I'll post the solutions to this. And then if you have any questions on it between now and Wednesday, please try and join my office hours or text me or call me. My number's on the syllabus. Okay. Yeah, so it's not open note. So for this test, I mean, what is it, by looking at the review, what is it that you actually need to know? I will give you the difference quotient, so you don't have to memorize that formula. I will give that to you. Quadratic formula. I'll give you the quadratic. I'll put it up on the board here if you need it. Other than that, I mean, formula-wise, it's just quadratic formula, difference quotient. Yeah, so this is yeah, not open note. So see, you know, my thing would be to study properly for this. You want to sit down with this and see if you can do things without having to constantly pull notes. And if you feel comfortable, just go, you know, go find another problem like it and see if you, again, can do it without picking up your notes. Maybe next to each problem, write down like what you need to do, steps, I don't know. No, any questions? Yes.
So what we did today, that's going to be on the exam.
That will not be on the exam, only in the form of a bonus question. So I may ask you to graph a function, right? Using transformations, right? Or look at this function and tell me, you know, what the shifts are, and that'd be a bonus. All right. Anything else? Online questions?